Very similar, very analogous would be gravitational potential energy. If I lift something up, I give it gravitational potential energy, which then means I've done work to it in giving it that energy. And moreover, if I were to let go of that, that potential energy that was there is going to convert itself into kinetic energy. That's very similar to how objects in a battery, electrons in a battery that don't want to be near each other because they're all negatively charged objects, are going to take advantage of that electric potential energy they have by being pushed close to each other to spring out of the battery and go into the circuit. Now, electric potential, similar idea, but there's no real analogy to this in terms of gravity. It's that same energy that we just talked about, but it's that same energy per unit charge that exists in a particular place in an electric field. So if I'm just at a random place in an electric field, it's how much energy a particular charge of, let's say, 1 coulomb would have if it were placed there. Or another way of looking at it, let's say back to our battery explanation, it would be if I have a battery and it's like, let's say, a 10-volt battery, that means that every particle in there has a energy of 10 joules per coulomb, which brings me to this part down here. This is a formula right off of your reference table. The units are joules per coulomb, which I have written here, or the more common unit would be volts, or just V. So here's a quick example of something you would see with volts that's not attached specifically to circuits. So you got an electron and is moving due to a potential difference of 20 volts. How much work is done? So we start with this. We know that this is 20. We're looking for work now. They say electron, so they inadvertently, or they indirectly told us the charge, because remember the charge of an electron is 1e, which is 1.6 times 10 to the negative 19 coulombs of charge. So we do that work. By bringing the 1.6 up, multiplying it by the 20. And you get 3.2 times 10 to the negative 18 joules. Moving on. The next one is current. That is the rate at which charge flows through a space. Typically a wire or some sort of a conductor, but it could technically flow through air in the real world as well. For instance, when you have a tremendous amount of buildup of charge in the cloud, you have lightning, which is just current that flows from the cloud through the air to the ground. Now, this is very important. In order to have current, you have to have a potential difference. So there has to be a situation when the electrons want to get away from each other. If I just have a random electron floating in space, it has no want to go anywhere. What I'd have to have is I'd have to have it near or in a negatively charged object, and ideally a positively charged object for it to go towards, in order for it to want to flow, in order for it to want to move from place to another. Okay, so current is the rate at which it goes from point A to point B. So it's charge per second. So the higher the current, the more charge that goes through a particular place in space in any given time. So coulombs per second would be my units, or amperes. Nobody ever says amperes. Everybody always says amps, or strictly A. So here's another example. Very similar question you would see current in that's not directly related to circuits. So they tell you the current is 10 milliamps. So milli is 10 to the negative 3. And the question says, how many coulombs of charge, so we're looking for charge, go by in 20 seconds. So the first part of this question, really simple. So we're going to say I equals delta Q over T. So we got 10 times 10 to the negative 3 amps, delta Q, 20 seconds. Multiply up. And you end up with 200 times 10 to the negative 3, not amps, coulombs, or 0.2 coulombs. Now, the second part of this question is a little bit trickier. Second part of this discusses the current, or rather the charge, in elementary charging. So, I know 0.2 coulombs, and I want to find out how many elementary charges, how many electrons that's associated with. So I'm going to say, set up a proportion. We got 1 coulomb. Well, that's 6.25 times 10 to the 18th.